Okay, thank you very much, and welcome back for this afternoon session. Now let's continue with second type of smoothing technique for analysis of time series data. In the morning session, we have seen different ways of models for time series data analysis, and we have seen the exponential smoothing method. So now let's proceed with the simple exponential smoothing method for time series data. So this simple exponential smoothing technique is the simplest of the exponentially smoothing method, which is naturally called as simple exponential smoothing, abbreviated as CES. So the method is suitable for forecasting data with no clear trend or with no seasonal pattern. If the data does not have any clear trend or does not have any seasonal pattern, so the simple exponential method could be used for analyzing these types of time series data. So as you can see from the figure here, the data in the figure do not display any clear trending behavior or any seasonality. So for such types of data, which does not have any clear trending behavior or with no seasonality variation, the simple exponential smoothing method could be used for analyzing such types of time series data. So as per the simplest or the simple exponential smoothing method, and especially by using the naive method, it is assumed that all forecasts of an outcome variable for the future are equal to the last observed value of the series. Like for example, all forecasted values of an outcome variable at the 10th observation, at the 11th observation, and maybe at the 12th observation are equal to the last observation before the 10th observation, that is the 9th observation. So that all observations other than the last observation will be lost, will not be considered for forecasting future outcomes of an outcome variable. So with a statistical formula, we can just express this naive method of the simple exponential smoothing as a value of an outcome variable y at time t given h interval is equal to the value of the last observation y at the last observation t. So for which h could be 1, 2, and up to n number of times that we call it the series. So the number of repeated observations. So hence the naive method assumes that the most recent observation is the only important one, and all previous observation provides no information for the future forecasting. So as per the naive method of this simple exponential smoothing method, the last observation will only provide an information for forecasting for the future outcome, and all previous observations will not provide any information. So this can be thought of as a weighted average where all the averages are given to the last observation, but except the last observation, all observations before that last observation will not be considered for forecasting of the outcome variable. So this is as per the naive method of the simple exponential smoothing method. So the second way is using the average method rather than the naive method. The naive method says that the last observation is only used for forecasting the future outcomes, and all other observations will be lost. But another way of using this simple exponential smoothing method is by the use of average method. So the average method of this simple exponential smoothing assumes that all future forecasts are equal to a simple average of all observations You see, so it considers all observations into account to forecast the future outcome. So the average of all observations will be used to forecast future outcomes of an outcome variable. So the formula will be the summation of all observations divided by the total number of observations. So for which H stands for the number of repeated measurements from 1 up to n maybe. So hence the average method assumes that all observations are of equal importance and gives them equal weight when generating forecasts, you know. So for generation or for forecasting for the future outcome of the outcome variable, value of the outcome variable, all observations will be given equal weight because they will be taken into account for forecasting the future value of an outcome variable by averaging of all observations, you know. So that is the average method of this simple exponential smoothing. But the naive method of the simple exponential smoothing method only considers the last observation to be used for forecasting future values of an outcome variable. And the remaining observations will not be considered in the naive method. But in the average method, all observations will be considered and the average of all these observations will be used for generating future forecasts of an outcome variable. So these are two extremities, you know. The one is only considering the last observation, and the next, the average method, is it considers all observations equally, you know, both the current values and the distant values are given equal weight. So that might not be, again, appropriate, you know. So we often want something between these two extremities. Another way of just simple exponential smoothing method, which could be in between these two extremes, would be appropriate enough, you know. So for example, it may be sensible to attach larger weights to more recent observations than to observations from the distant past, you know. So giving more weight for recent observations is better than giving equal weight for the distant past events and for the current observations. So there should be something which take into account this consideration, you know. Okay, so this is exactly the concept behind simple exponential smoothing. So in the case of simple exponential smoothing, it gives weight for all observations, but the weight given for the recent observations is much higher than the weight given for the distant past observations. So that is the simple exponential smoothing method. So forecasts are calculated using weighted averages, where the weights decrease exponentially as observations come from further in the past. So the weight given for the past observations will be much less than the weight given for the recent observations. So that is the idea or the consideration of this simple smoothing or exponential smoothing method. So the smallest weights are associated with the oldest observations, and the highest weights will be given for the recent observations. So to account this idea into consideration, here is a statistical formula to calculate this simple exponential smoothing method by taking account of giving much weights or larger weights to the recent observation and less weight for the oldest observations. Okay, so within this formula there is a constant term that is the smoothing constant alpha. We do have the outcome variable or the forecasted outcome variable y hat at time t plus 1 in the future, given the current value of t is equal to the smoothing constant alpha multiplied by the value of the outcome y at time t plus alpha multiplied by again 1 minus alpha multiplied by y at t minus 1, the previous observation, and then plus alpha multiplied by 1 minus alpha square multiplied by y at t minus 2. So this will continue till the last observation, you know. So by squaring, this square will make the weight given for the oldest observations to be get less and less. So this is a way, you know. So this alpha will be always in between 0 and 1, the smoothing constant. So the one step ahead forecast for time is a weighted average of all of the observations in the series. So all observations will be given a weight, but the rate at which the weight decreases is controlled by the parameter alpha, that is the intercept. So the recent observation will just gain higher weights, you know, this one, because there is no squaring over here. So that will be having higher number or larger number or a higher weight. But the next, the oldest observation, that is t minus 2, is being squared, you know. So this fraction of number, when it is squared, it will be just get lower and lower. So the weights given for the oldest observations will get smaller and smaller than that of the current observations. So that will be controlled by the smoothing constant, that is alpha. So the table below in the next slide shows the weights attached to observations for different values of alpha when forecasting by using a simple exponential smoothing method. So in order just the forecasting was made by using a simple exponential method, you know. So note that the sum of the weights even for a small value of alpha will be approximately 1. If you sum up all the weights that have been given for all observations, so the sum of the weights will be finally 100%, or it will be 1. So have a look at on this table, you know. So now we do have an outcome variable which is going to be forecasted at time t, and there are preceding observations, previous observations before this time. So like for example, if yt is the 10th observation or the 10th visit, then y at t minus 1 will be the 9th visit, t minus 2 will be the 8th visit, and t minus 3 will be the 7th visit, and t minus 4 will be the 6th visit, and t minus 5 will be the 5th visit, in such a way, you know. So this t minus 5, the 5th visit is older. This is the oldest among all these observations. So the weight which will be given for the 9th observation will be much higher than the weight given for the 8th observation, and the weight given for the 8th observation or visit will be much higher than the weight that will be given for the 7th visit. So in this way, so this weighting will getting decrease, you know. Look over here, for example, for the y at time t, the weight is now, like for example, if alpha is the constant smoothing, the smoothing constant is 0.2. If it is 0.2, so that's for the current observation, the value will be 0.2, or the weight. So then after, for the previous one, it will get decreased, you know, 0.16. And then for the next one, it gets decreasing again. And then for the next again, it is decreasing. Now it is decreasing. So you see, so the weights that are be given for each observation will get exponentially decreasing and decreasing. So the oldest observations will just be given a lower weight than the recent observations. If, like for example, if the constant, the smoothing constant alpha is 0.4, so the weight given for the current observation will be 0.4, and then for the oldest, step by step, the weight is getting decreasing, you know. When the intercept is, or the constant is 0.6, for the current one it is 0.6, and then sequentially it gets decreasing, you know. And even when it is 0.8, you can have a look at. So exponentially, the weight given for the contribution of each sequence of measurements gets decreasing and decreasing over time. So this is the way how the simple exponential method will just forecast the outcome of the future outcome of a variable. And this is actually this calculated values in the table, once if the alpha is given, is calculated by the previous formula that we have seen here in the slide. So by replacing the alpha that have been given, we can just calculate the values indicated in the table by using the formula over here. So this is the way how the simple exponential smoothing method forecasts the outcome or the future outcome of an outcome variable, or the future value of an outcome variable, sorry. So for any smoothing constant alpha between 0 and 1, the weights attached to the observations decrease exponentially as we go back in time. And hence the name exponential smoothing is given, you know. That is why it has been named as exponential smoothing, because the weights given for the oldest observations are getting exponentially decreased and decreased. If the smoothing constant alpha is small, that is close to 0, so more weight is given to observations from the more distant past one, because when it is close to 1 minus a small number will be just having a higher number, you know. And to the contrary, if the smoothing constant alpha is large, which is close to 1, 1 minus 0 will be 1. So more weight will be given for the more recent observations. For example, for the extreme case, if the alpha, the moving constant, is 1, then finally the forecasted future outcome will be just the value of the previous last observation. Exactly, it will be. Why? Because if you substitute number 1, if alpha is 1 within this formula, if you substitute 1, if alpha is equal to 1, for example, over here, let's replace or just use a value of 1 in place of alpha, or substitute alpha with 1 if alpha is 1, that means. So 1 minus 1, it will be 0, you know. So 0 multiplied by this 1, this alpha, and this number, it will be, this value will be 0. And then now, again alpha is 1. 1 minus 1 is 0. 0 square, 0. 0 multiplied by this alpha and this number, it will be 0. So 0 plus 0, it will be 0. So what will be left is only alpha is 1. So 1 multiplied by y at t. So this will be exactly as the same as we see this one. Okay. So that means all contributions or weight is 100%, the weight is given for the last observation, simply, if alpha is 1. Okay, and the forecasts are equal to the naive forecasts. That means the naive method said that the forecasts of the future outcomes, so the future values of an outcome variable is exactly the same as the last observation, it says. So finally, if alpha is 1, then it will be just exactly the same as with that of the naive method. The naive method. Okay, now we are approaching to the last session of the theoretical idea of this time series analysis, you know. The most important and final component of this time series analysis is the time series decomposition. Time series decomposition. So time series data can exhibit a variety of patterns. You see, once you have longitudinally measured time series data, those repeatedly measured data will have a variety of patterns, a number of patterns, different patterns will be there. So we need to just identify those patterns one by one, you know. We need to decompose the patterns by grouping, you know. So different groups or different patterns will be there. So identification or breaking down of those different patterns is said to be decomposition. So it is often helpful to split or to break down a time series into several components, so that each component, the breakdown components, representing an underlying pattern of category. When we decompose the several patterns or varieties of patterns into different components, each component will represent a specific underlying category of or pattern of category. So that is the idea of decomposition of time series data. Why we decompose? Because these time series data have a variety of patterns. So in order to have a breakdown of different patterns category by category, we decompose those time series data. So when we decompose a time series into components, we usually combine the trend and the cycle into a single trend cycle component, you know. So the trend and the cycle will be just combined into a single trend cycle component. So, and for simplicity, we say simply trend, you know. But in one component, there will be always trend and cycle. So the trend and the cycle of the pattern of the data will be just combined to make one component. So we think of a time series as comprising of three components. So the decomposed time series finally will have three most important components. The first one is a trend cycle component, the trend cycle component. The second one is a seasonal component, and the third one is a reminder component. So this reminder component is containing anything else in the time series other than the cycle, the trend cycle component and the seasonal component. So once we have just formed the component or decomposed the time series data into components, each of the decomposed components will have three most important components: the trend cycle component, 1, the seasonal component, 2, and the remainder component. That remainder component is containing anything else in the time series data, you know, other than the trend cycle and the seasonal components. Okay, so how do we decompose time series data? What are the tests or the techniques of decomposition of time series data? The first one is the classical decomposition method, you know, the classical decomposition method. In the case of a classical decomposition method, we assume that the seasonal component is constant from year to year. Because as we have said before, a decomposed component will have three components. One, a trend cycle component. The second one is a seasonal component. And the third one is the remainder component. So in the classical decomposition method, what it assumes that it assumes the seasonal component of the decomposed time series data is constant from year to year. The seasonal component for any data is constant from year to year, according to the classical decomposition. So in the classical decomposition method, there are two forms of classical decomposition: additive decomposition and multiplicative decomposition. It has been. So there are these are described below for a time series with a seasonal period M. The seasonal period M. Now M stands for the seasonal period, and we labeled M for M. The seasonal period M is equal to 4 if the seasonal variation is by quarterly. The quarterly seasonal variation is labeled as 4. M will be T12 for monthly data, and the seasonal period M will be 7 for daily data or for weekly pattern. For daily data with a weekly pattern, you know. So if the seasonal period is within a week, so the seasonal period M will be 7. If it is monthly data, so the seasonal period M will be 12, you know. And if we are just trying to just decompose or to see the pattern by quarterly data, then the seasonal period M will be 4. That is according to the additive decomposition method. For multiplicative seasonality, the M values that form the component are sometimes called seasonal indices. So M is now standing for the seasonal period. So in the case of multiplicative seasonality, the M, that is the seasonal period M, which forms the component are said to be seasonal indices. So if we are assuming an additive decomposition method, then we can rewrite the decomposition of an outcome variable y at time t is equal to st plus capital TT plus capital RT. So where yit is the data, the measured data at time t, the st is the seasonal component, and the TT is the trend cycle component, you know. So according to the additive decomposition method, the data, that is the decomposed data y at time t, is equal to the seasonal component st plus the trend cycle component TT plus the remainder component RT. So that is the additive decomposition the additive decomposition method of the classical decomposition, you know. Alternatively, for a multiplicative decomposition, we could write the decomposition as the data y at time t is equal to the seasonal component st multiplied by the trended cycle component TT multiplied by the remainder component RT. So this is a multiplicative decomposition method of the classical approach, you know. If that is a additive, it will be the summation of the three components. Okay, so the additive decomposition is the most appropriate if the magnitude of the seasonal fluctuations or the variation around the trend cycle does not vary with the level of time series. If the seasonal fluctuations or the variation around the trend cycle does not vary over a period of time, so the additive decomposition is appropriate. But when the variation in the seasonal pattern or the variation around the trend cycle appears to be proportional to the level of the time series, or that means if the seasonal pattern variation or the variation around the trend cycle is not constant over a period of time, so that the multiplicative decomposition is appropriate. So these are the conditions when the additive decomposition and the multiplicative decomposition will be used, you know. So to use the additive decomposition method, the seasonal variation or the variation around the trend cycle should not vary over time. It should be constant. And to use a multiplicative decomposition method, the variation around the trend cycle or the seasonal variation should vary over a period of time. That should be proportional to the level of time series. So in that case, we will use the multiplicative decomposition method. So an alternative for using a multiplicative decomposition is to first transform the data until the variation in the series appears to be stable over time. So if the seasonal variation or the variation around the trend cycle is changing over time, we can then transform the data until that variation becomes stable. So that by transformation, if we make the data to be stable, then we'll go for additive decomposition. Because by transformation, we make the data to be stable. So after making the data to be stable by transformation, we can use the additive decomposition. That is the alternative way of multiplicative decomposition, you know. So when a log transformation or a logarithmic transformation has been used, this is equivalent to using a multiplicative decomposition. Why? Because the outcome variable at time t, according to the multiplicative decomposition, is equal to the seasonal component multiplied by the time trended cycle component multiplied by the remainder component, is equivalent to mathematically the logarithm of the outcome variable y at time t is equal to the logarithm of the seasonal component plus the logarithm of the trended cycle component plus the logarithm of the remainder component. So mathematically, this logarithmic transformation could be just replaced with this one. So that is an alternative way of just multiplicative decomposition into additive decomposition, you know. So here are the steps. How the additive decomposition is done and how the multiplicative decomposition will be made. So in the first step, what we are going to do, or what the software is going to do is, if m is an even number, so m stands for now, what we have said is, m is standing for seasonal variation. The seasonal variation, it could be 7, it could be 12, it could be 4. For quarterly seasonal variation, m will be 4. For monthly data, it will be 12. For weekly data, it will be 7. So m here stands for seasonal variation. So if m is an even number, instead of being 12 or instead of being 4, if it is instead of being 7, if it is 4 or 12, that is, if it is an even number, the seasonal variation m, if it is an even number, we compute the trended cycle component labeled as t hat at time t. T hat at time t is now representing the trended cycle component. This one. The trended cycle component will be calculated by using 2 multiplied by m moving average. So we will use, or we will multiply this m by 2, and then a moving average calculation method will be made. So the trended cycle component t hat at time t will be calculated by using this formula, you know. 2 multiplied by m with a moving average method, the moving average that we have seen in the morning session. So the trended cycle component will be calculated by using this formula. The trended cycle component is now labeled as t hat at time t. But if m is an odd number, if it is an odd number, we calculate the trend cycle component using m with moving average without any multiplication of 2, you know. So now m will not be multiplied by any number. Simply that m moving average will be used to calculate the trend cycle component. So m number of moving average, like for example, if m is if m was 2, like for example, it is now even number. So 2 multiplied by 2, which is 4. So a 4 moving average will be used to calculate the trend cycle component. A 4 moving average. For the 4 consecutive data series, moving average will be calculated. So by that, we can get the trend cycle component. But if m is, for example, 3, that is now it is odd. So a 3 moving average method will be used to calculate the trend cycle component. The 3 moving average. If it is 7, 7 moving average method will be used to calculate the trend, that is to calculate the trend cycle component, you know, which is labeled as t hat at time t. Now that is the first step. The second step, by having this trend cycle component, we need to calculate the trended series. The trended series by the outcome variable y minus the trend cycle component, which was calculated over here. So this will be the calculation of the trended series, the second step. Now after calculating this trended series by using this formula, and this t hat at time t is the trend cycle component, which is obtained by either by this one or by this one, when it is odd number and even number. Now the third step, to estimate the seasonal component for each season, simply average the trended value for that season. We need to average these all trended series finally. The average of the trended value will be used to estimate the seasonal component for each season. For example, with monthly data, the seasonal component for March is the average of all the trended March value in the data. The trended value for all March, for all the dates during March will be the averaged, you know. So the average will be used to estimate the seasonal component. Now, these seasonal component values are then adjusted to ensure that they add to 0. All the seasonal components, when we add all these seasonal components, then that will be 0, you know. So the seasonal component is obtained by stringing together these monthly values and then replicating the sequence for each year of the data. So that will give the seasonal component ST. Now, in the first step, we have calculated the trended cycle component, and then in the second step, trended series has been calculated. The trended series was used to just calculate the average value in order to get the seasonal component S hat T. S hat T is now the seasonal component. So the seasonal component will be calculated, and then the trend cycle component will be calculated. And then the remainder component RT is anything else other than the trend cycle component and the seasonal component, which is the third component of the decomposed data. So this is the way how just the classical or the additive process is being done. In the last step, the remainder component is calculated by subtracting the estimated seasonal and trended cycle component. So the remainder component will be calculated by subtracting the seasonal and the trended cycle component. So the remainder component RT is equal to the outcome variable Y at time t minus the trended cycle component minus the seasonal component. So this is the way how just we can calculate the remainder component, the seasonal component, and the trend cycle component. So these are the three components for any decomposed data. According to the additive classical decomposition method. For the multiplicative decomposition, a classical multiplicative decomposition is similar, except that the subtractions are replaced by divisions, you know. In the additive, we just subtracted, but in the case of multiplicative, the subtraction will be replaced by the division. Like if m is an even number, so we compute the trend cycle component, that is t hat, by using 2 multiplied by m moving average, that is the same. And if it is odd number, again the trend cycle component will be calculated by using m moving average. This is the same hereafter. The difference is hereafter in the second step. Calculate the trended values by dividing the y value or the outcome value by the trend cycle component. So that is the division. So the trended series will be calculated by dividing the outcome variable y, the y value, by that of the trend component cycle over here. That is the trended series. So from this trended series, to estimate the seasonal component for each season, simply average the trended values for that season. That is the same with the additive one. For example, again, with monthly data, the seasonal index for March is the average of all the trended March values in the data. So these seasonal indexes are then adjusted to ensure that they add to m value, you know. When we add them, then that will be m value. Okay. Now, the seasonal component is obtained by stringing together these monthly indexes and then replacing the sequence for each of the data. That is the same. So the average of this detrended series will give us the seasonal component. So the seasonal component will be calculated by averaging of the detrended series. The detrended series that we have seen in the previous slide, over here. The value for the outcome variable y divided by the trend cycle component t hat. So the average of all these values will be used to calculate the seasonal component. And then finally, the remainder component RT will be the division of the two. The y, the outcome variable y, the value for the y divided by the trend cycle component multiplied by the seasonal component. So the division of the two will be used for calculation of the remainder component. So this is the way how the classical decomposition method decomposes time series data into different components by using either the additive method or the multiplicative method. Okay, another way of decomposition of time series data is, by using X11 decomposition. X11 decomposition. So this is another popular method for decomposing quarterly and monthly data. So the X11 method is used to decompose a quarterly data or a monthly data. So that means if you do have a number of time series data, so X11 will decompose your data in terms of quarterly or monthly. So that is the way. So this method is based on classical decomposition, The method is based on the classical decomposition. But it includes many extra steps and features in order to overcome the drawbacks of classical decomposition that were discussed in the previous session, In particular, the trend cycle estimates are available for all observations, including the endpoints. And the seasonal component is allowed to vary slowly over time. You see? In the case of classical decomposition, it is assumed that the classical variation is constant over time. But in the case of X11 decomposition, it is assumed that the seasonal component is allowed to vary slowly over time. So this is the advantage of the X11 decomposition, which overcomes the drawback of the classical decomposition. Because the classical decomposition assumes that the seasonal component is constant over time. Okay. Now, X11 also has some sophisticated methods for handling trading day variation, holiday effects, and the effects of known predictors. It can be used for just control the effects of known confounders or predictors. And it can also handle both the additive and the multiplicative decomposition. That is the X11 method. In the X11 method, there is also the additive and multiplicative decomposition. The process is entirely automatic and tends to be highly robust for outliers. So it can control the effect of outliers, and it can just loosen the assumption of constant seasonal component. So that is the X11 method. So in the X11 method, there is no assumption for seasonal component constant over time. It can vary slowly over a period of time, And even it can just be used to just handle the effect of predictor variables. The other way of decomposition is the SEATS decomposition. SEATS. This stands for seasonal extraction in ARIMA time series. The abbreviation for seasonal extraction in ARIMA time series model, So the SEATS decomposition procedure works only with quarterly and monthly data again. So seasonality of other kinds like such as daily data seasonality or hourly data seasonality or weekly data seasonality will require an alternative approach. So the SEATS decomposition and the X11 decomposition are just used for quarterly and monthly data decomposition. And the next one is the ACTL decomposition method. The ACTL decomposition has several advantages over that of the classical decomposition, over the CITES decomposition, and over that of the X11 decomposition method. Why? Unlike the CITES and X11 decomposition, the ACTL decomposition will handle any type of seasonality. So there might be any type of seasonality variation, you know, and it might be used for hourly decomposition data, weekly, daily, monthly, quarterly, yearly, whatever. It can handle any type of seasonality, not only for monthly and not only for quarterly data. So the seasonal component is allowed to change over time again. You see, the seasonal component is not assumed to be constant. So there is a seasonal component variation over time. It is allowed to vary, and the rate of change can be controlled by the user by using this ACTL method, you know. So the smoothness of the trend cycle can also be controlled by the user. The smoothness of the trend cycle and the smoothness of the component or the seasonal component can be controlled by the use of this ACTL method. It can be, again, robust to outliers. That means the user can specify a robust decomposition so that occasional unusual observations will not affect the estimate of the trend cycle and the seasonal component. So the outliers will not affect the seasonal component and the trend cycle component because the ACTL decomposition method can handle outliers, you know. So really it is very important, and it can be used for any type of data. So they will, however, affect, the ACTL decomposition method will affect the remainder component, you know. The outliers, even though the outliers cannot affect the trend cycle component and the seasonal variation component, but the outliers will affect the remainder component. So on the other hand, the ACTL also has some disadvantages. In particular, like it does not handle trading day or calendar variation automatically, you know. If there's any daily variation or calendar variation, and it only provides facilities for additive decomposition. It only uses or just allows us to use an additive decomposition method, you know. Okay. So these are all about the time decomposition or time series decomposition methods that will be just used in any software maybe. We'll see them in SPSS actually. And then finally, let's have a look at on the model fit statistics. All the modeling methods that we have seen will be just determined by the use of model fitness statistics. Which of the alternatives that we have seen will be the best is determined by using the model fitness statistics. The first one, or the first criteria for model fit statistics for any of the modeling methods for time series analysis is a stationary R square. The stationary R square. The usual R square that you know in any regression analysis is now named as a stationary R square because in time series analysis data we have an assumption that the data is stationary. So that the R square is named as a stationary R square. So a stationary model is effectively one with the trend removed. That means it does not have any trend. So that the values have the same variance and the same mean over time. So larger value of this stationary R square will indicate a better fit. The larger the value for the stationary R square is, the better the model fitting or the better the model fitness. And the second criteria is the root mean square error, RSME abbreviated as. Root mean square error. So squared errors are based on the square of the differences between the fitted value and that of the observed value. And you are familiar actually with it in linear regression, the method of least square. So it is similar to a standard deviation value, you know. So smaller values of this root mean square error indicates a better model fitness. So the lower the root mean square error, that is the better the model. Another criteria is the mean absolute percentage error, abbreviated as MAPE. The average error values in percentage terms, you know. So it is in the case of in terms of percentage. So values such as 0.15 or equal to an average of 15% or that, below that. So smaller values of this MAPE is an indication of better model fitness. And the fourth type of model fitness criteria is the mean absolute error, abbreviated as ME. Again, the mean of the absolute values of the forecast errors. So mean absolute error is the same unit as the dependent series. That means this is appropriate when the cost of the forecast errors is proportional to the absolute size of the forecast error. And actually, the smaller the value for this mean absolute error is, the better the model fitness again. Okay. Another additional criteria is the maximum absolute percentage error. Again, the maximum absolute percentage error, the smaller the value is, the better the model. And the next one, the maximum absolute error. Again, the maximum absolute error, the smaller the value is, better the model fitness. And again, the normalized BIC, normalized Bayesian information criteria. Again, the smaller the BIC or the normalized smaller BIC value is, the better the model fitness. And the last one, the Akake information criteria and the Schwarz information criteria. So again, the smaller the values for the Akake information criteria and the Schwarz information criteria is a better model fitness. So these are the model fitness criteria. So now, how do we select out of all possible time series data analysis models, what will be the best and the easiest way of model selection by considering these model fitness criteria? Are we going to just try each of the models by ourselves, or is there any easy way or method of just identification of the right model? That is by the use of the expert modeler in the SPSS especially. So the method of modeling, if you choose the expert modeler or expert modeler, the expert modeler will try each of the modeling types available for the time series data analysis, and it will identify the best fitting model. So we are not going to try each and every models in time series analysis, you know. Rather, we order the software to use the expert modeler so that the expert modeler will identify the best fitting model among all the alternatives. So that is the easiest and the simplest way of just identifying the right model for our time series data. So based on a measure of model fitness criteria that we have seen previously, the expert modeler will try a number of model types, and then it will select one with the best fit over the series of models, you know. So this is really the very fantastic and the easiest way of identifying the right model for our time series data analysis. So this is the way how just I want to just wind up this session for you. And then finally, when analyzing a time series data, we need to consider all these things, you know. During the analysis of a time series data, we need to consider these questions. And we need to ask, are the data points regularly spaced or not? We need to ask and answer this question. And how far can I forecast into the future? How far? Is it for 5 years, for 10 years, or for 15 years? For how many years can we forecast into the future? And what is the periodicity? Should I exclude any data? Is there any missing data? How the missing data will be handled? This should be asked and answered, you know. Do I have any other predictor variables? Do I have independent variables or predictor variables which is going to be fitted with the time series data analysis? Are there special events that need to be marked? And do I need to forecast more than one series? That means more than one outcome variable? All these questions should be taken into consideration when we are just trying to or planning to analyze a time series data analysis, you know. So this is all about the theoretical idea of a time series data analysis. In the next session, we'll see demonstration of time series data analysis with example data sets.